Hey, hey, hey. Are you guys ready for another sweet calculus lesson from your own Miss Vaught? So last video, last class, we talked about differentiating inverse trig functions. So of course now, the next thing we would do is anti-differentiation integrating inverse trig functions. So I've written up here the three common forms that we'll see. We generally don't deal with cosine, cotangent, and cosecant as much because they're just the negatives of, sine, tangent, and secant. And so we could do a little kind of u sub manipulation or maybe pull the negative sign on the outside of the integral if we ended up with one of those forms. So we just focus on these three forms right here. And really the biggest deal when you are when you're integrating um, these types of forms is that you just need to set up your algebra correctly so that you can then integrate, which is kind of, the idea, what you have to do for most integration. But in this case, you really have to use some probably algebra that you haven't used in a while. So I thought I would start by going over some algebra with you, some things that you would need to know. All right, so methods of algebraic manipulation. There we go. I can write. So the first one I would call factoring out the constant term. So we had an integral that looked something like this, or this is the function that we were integrating. So I have this function here, and I see that it really looks like the derivative of arctangent. So I really want to be able to integrate it and have it be arctangent. But I have this 4 right here, and our derivative of arctangent has a 1 plus x squared. So what I can't do is I can't just say, 1 over 4 times 1 over 1 plus x squared. That's not right. Because if I were to distribute that 4 back through, I would get 1 plus, or 4 plus 4x squared, which is not what I started with. So what I'd like to do is I'd like to factor the 4 out of both terms. Now I know that there's not a 4 in the second term, so we're just going to manipulate that second term just a little bit so that we're able to factor a 4 and put it on the outside. So we're going to take this 4 and we're going to put it on the outside. That, of course, is going to make the first term 1. But when we factor something out, what we're really doing is just dividing everything by 4. So it ends up that we get x squared over 4 there. And you can always check this just by distributing back through. There you get 4. Here the 4's would cancel on the second term and you'd get x squared. So we end up with what we start with. All right, there we go. So now we always have to write this as one whole thing squared. So we need it as something all squared. And I know that I can take and square 2 and get 4. So I can rewrite this as, I'm going to put this 1/4 totally on the outside. That 1/4 would go on the outside of your integral if you were really integrating this. We're just setting up the algebra. And now what would happen, just kind of like I said, this would go on the outside. And then this thing right here, we would have to do u sub because, we don't just have an x there. And the derivative of that thing inside the parentheses is not 1. So when the derivative of a term like that is not 1, we have to use a u sub. So we would let u equal x over 2. And then what's going to happen is that we just get that du would be 1/2 dx. because that's just 1/2 times x. And so constant times x is just the constant. And so then we would just move and get 2 du is equal to dx. And then this 2 would also go on the outside of the integral along with the 1/4. And you could simplify it and get 1/2. Right, so this method works pretty similarly. I'm not going to go into as much detail as the other one, but if you have a square root, like the derivative of arc sine x, you can use a similar method. So let's take a look at this. So we're just setting it up. We're not actually going to integrate anything. So if I had something like this, 2 divided by the square root of 9 minus x minus 1 all squared. So I see that this looks pretty similar to the derivative of arc sine x, but I have this 9 here. This in parentheses is okay. We can have a function in parentheses, but this has to be a 1. And there was even an example, I believe, that I worked where what I was factoring out wasn't a perfect square, and we ended up with a square root of 3 or square root of 2 or something, and that's okay. But this one will work out nicely because it's a perfect square. All right, so just like on the problem up there, I want to factor the 9 out of both these terms, and so I have a 2 on the top. Remember, this isn't just a 9, it's going to be a square root of 9. And then that'll be 1. And then this will be x minus 1 all squared divided by 9. And then just like before, oh, I need a square root on all this. Just like before, I will have to take this term and make it all one thing squared, because that's what it looks like in the derivative of arc sine x. So I have just one more thing that I need to do. This will be 2 divided by 3. I'll go ahead and take the square root of 9, and then this becomes, I keep forgetting my square root there, the square root of 1 minus, all in parentheses, x minus 1 divided by 3 all squared. And then just like before, this is not a negative sign, this should be connected here. Just like before, we have that constant 2/3, so the 2/3 can go on the outside of the integral if we were integrating this, and then we could let u be x minus 1 over 3, and it looks pretty complicated, but it's just 1/3 times x minus a third, so the minus a third will just become 0, and so the derivative of 1/3 times x is just 1/3, so we just get 1/3, du is 1/3 dx, and then you just set it up. We don't have a 1/3 there. I guess we kind of do, but I would just do 3 du is equal to dx, and then we would also put that 3 on the outside of the integral, and it would actually make that denominator and 2/3 cancel. All right, so let's take these methods and let's apply them to some integrals. There we go. So we have this problem right here, the integral of 7 all over 16 plus x squared dx. So see a few things. I don't have a square root in my denominator. I just have a number plus x squared, so this makes me think I'm going to use arctangent. I noticed that this is not 1, the 16, so I'm going to have to use the method that we just talked about to factor the 16 out. And then, so let's go ahead and set it up. So we're going to have a 7 over 16. I'm just going to go ahead and put that there. I guess I could have put it on the outside of the integral, but I'll do that next time. And then this becomes, in the parentheses, 1 plus x squared all over 16, and then my dx. So I'm going to go ahead and I'm going to pull the 7 over 16 and put it on the front of my integral symbol. And then I'm going to do 1 over 1 plus, and we have to make this one thing all squared. So this becomes x over 4 all squared, and then your dx. So I have 1 plus something all squared, and the derivative of that something is not 1. So I am going to have to do a little u sub, and I'll write it over here. So I'm going to let u equal x over 4. And then remember the derivative of that is just 1/4, because it's just 1/4 times x. And then, I don't have a 1/4 in my integral, so I'm just going to multiply both sides by 4, and I get 4 du is equal to dx. This 4 will go on the outside of my integral. Change this view just a little bit. Actually, no, I'll leave it the way it is. So I end up with 7 over 4, because the 4 on the top and the 16 would cancel. And then I have the integral of 1 over 1 plus u squared du, which is arctangent. So I just need to, once you get here, you just integrate, 15 steps of algebra, 1 step of calculus. That's always how it works. And then this would be arctangent of u. So I'm just going to go ahead so I don't have to write it down twice and plug in my u. And then, of course, you need your c. See, not so bad, huh? You just got to set it up, and then the integral is really easy. Okay, so let's do another example. So let's try this right here. This is a little tricky. I had to stare at this one for a minute to think about what I would do. So I see I have x squared plus 1 in the denominator, which is super nice because I don't have a extra constant. I know, 1 over x squared plus 1, I could integrate that very easily and get arctangent. But I have an x minus 3 on the top. So I think, well, maybe I'm supposed to use u sub, and I'm supposed to let u equal x squared plus 1. Because I have an x on the top. But if you do the derivative of x squared plus 1, you get 2x, and I don't know what to do with that stupid 3. So then I was like, oh, well, what if I split my fractions? Because I can write this as x over x squared plus 1, and then I don't even need to use arctangent there. I can use u sub. So that's dx. Plus the integral of 3 over x squared plus 1. And that's pretty easy because I can just take the 3 and put it out front, and I have 1 over x squared plus 1, which is arctangent. So let's do it. Let's let u equal x squared plus 1, and then du is 2x dx. And then we get 1/2 du is equal to x dx. Y'all like my fun voice. This will up top become, I have the x dx right here. So I just need to put the 1/2 out in front, and that's just going to be 1 over u, right? Because u is x squared plus 1. And then over here, I don't even need to use u sub on the right-hand part, because I can just pull that 3 out, and then I've got 1 over x squared plus 1, which is arctangent. So let's integrate. Remember the 1/2. The 1/2 has to go on the front, and we get 1 over u du plus 3 times the integral. Go ahead and write this out, x squared plus 1 dx. I sound so excited, don't I? I am. I'm always excited about calculus. So we have 1/2 times the natural log of the absolute value of u. And remember, u is x squared plus 1. The absolute value signs are kind of redundant because x squared plus 1 will always be positive. But I'll put them there so you don't forget on another problem. And then, this 1 over x squared plus 1 is just arctangent. So we have arctangent of x. Oh, the 3 in front, don't forget that, plus c. Woohoo! So fun. So once we realized, hey, we can split our fractions and we've got stuff we can work with, it was a pretty easy problem. Okay, so I have another one. Actually, no, I'm not going to do that one. I want to talk about another method of algebraic manipulation. And y'all have learned this before. I'm sure you don't remember, but you know how to complete the square. So let's check this out. We want to take something that looks like this. We're going to do this problem. We're just going to complete the square, and then I'll show you how to integrate. And we want to make it look like something like this. 1 over x, and then it'll be plus minus something. I'll use a question mark, all squared. And then it could be plus something else. We do want it to be plus here, because if it's minus, we can't use arctangent. This also works for sine and cosine if it's under the square root. Or sorry, sine and secant if it's under the square root. Then we would want minus. Most of the problems I've seen have dealt with arctangent because there haven't been that square root there. Can make things a little tricky. Alright, but let's take a look at this. So, I don't know if y'all remember how to complete the square, but what we want to do is we want to add something over here and subtract it so that whatever we add will make these first two terms a perfect square. How I always taught my kids in the past is you take this middle number, I call it b, and if you do b over 2 all squared, that's always going to be the c that you need to add on. So 6 divided by 2 is 3. 3 squared is 9. So I'm going to have to add 9 and subtract 9. And then that will give me a perfect square. And I kind of write it in parentheses like this. I get 1 over x squared plus 6x plus 9. There's my perfect square. And then don't forget the 13 that's there. That'll screw you up. Oops, I need the 1. And then I have to subtract that 9 that I added. There we go. And then now I'm going to do a little more algebra, and I end up with 1 over x plus 3 all squared plus 4. Now I'm going to show you the next step because it's what we did before. If I wanted to do arctangent, if I wanted to set this up to integrate it so it's arctangent, that's what I want to do. I need to make this 1. So I factor the 4 out of both terms. And it doesn't matter that you have an x plus 3 up here, kind of like in the previous problem. You can just divide that by 4 and it will work beautifully. So we have 1 over, we've taken the 4 out, right? And so here we have x plus 3 all squared divided by 4 plus 1, because we factor the 4 out. And then we get 1/4, let's write this over here actually, times 1 over. And then now remember we have to make this all one thing squared. So we're going to take the 4 and bring it under the squared and it'll become a 2. Yeah, I don't really need this parentheses here. There we go. And now we've set it up to integrate. And you know, of course, just like on the previous problem, we would let u be x plus 3 over 2, and then we'd find our du and set it all up, and it would work out lovely. So I want to show you an example. So this is a definite integral. I need my pen. So we're going from 0 to 2 of dx all over x squared minus 2x plus 2. So I want to set it up so that I have a perfect square. So look at these two terms. My b is -2. So I have -2 over 2 all squared, which is -1 squared, which is 1. So I want to add 1 and subtract 1. Dx all over, let's see, what will this be? We have x squared minus 2x plus 1 plus 2 minus 1. Don't forget, you know, I'm adding this. You add and subtract the same number. Alright, so let's set it up. So this becomes the integral from 0 to 2 dx all over x minus 1 all squared plus 1, because 2 minus 1 is 1. Now this is cool because this is 1, so we don't have to do anything. And the derivative of this is 1 also, so we don't even have to use a u sub. We're just going to do the arctangent of x minus 1 from 0 to 2. So let's do that. Oh. So we have arctangent of x minus 1. Don't do plus c, right, because it's definite. From 0 to 2. So arctangent of 2 minus 1 is arctangent of 1, which is pi over 4. Arctangent of 0 minus 1 is arctangent of negative 1. Arctangent is only defined from negative pi over 2 to pi over 2, so this is going to be minus negative pi over 4. And this gives us pi over 2. Pretty easy stuff. Alright, I hope y'all will be ready for your next lesson. And if you would like to try some problems before you come to class, this is going to be your homework that we're going to work on. I guess I'll call it classwork. CW. So we are going to be in section 5.7. I don't know the exact page number, but we're going to do 2 through 30 every other even. I hope that makes sense. And then we're going to do, I didn't like 34, so I kind of shuffled things around. So I have 32, 36, 40, and then I really liked 68, so I threw it in there. Okay, so I'll see you guys next time.